Welcome back, everybody. Mr. Johnson with you, of course, once again. This is the second of two lectures on section 1.5 from our AP Chem 2 book, Integrated Rate Equations. And this one will focus specifically on just solving problems. We'll do a problem similar to the one that we did at the end of the last lecture, and then a couple of new types of problems. Sit back, relax, and enjoy the ride. So I've jumped ahead. We're on page 61 of the ebook, looking at the second practice problem here, where nitrogen dioxide decomposes into nitrogen monoxide and oxygen gas. That's the reaction we actually saw in the last video. Student collects the following data. It's concentration against time that's collected. That's typically the data that's collected. And then we've got columns here for natural log and inverse of concentration. Asks us to draw three graphs and determine the rate law expression and the rate constant with units for the decomposition of nitrogen dioxide. So I'm going to take us to Excel, where I've generated a table like this to have Excel calculate natural log and inverse concentration for us. And then we'll ask Excel to graph it for us, figure out what the order is and what the rate law constant is, and then write the rate law. So here we are in Excel. This is the same data we just saw, time, and then the concentration of nitrogen dioxide alongside it. I'm going to have Excel calculate natural log for me. I want to remind you that if you want Excel to calculate something for you, put an equal sign in. Abbreviation for natural log in Excel is ln, and I want it to take the natural log of the value that's in B2. So I click on it, end parentheses, and there's the natural log of B2. Remember, this square in the lower right-hand corner is the autofill. If I use my mouse and drag it down, or I double-click my left button, it will calculate the natural log of all of the adjacent values. So there they are. Going to do the same thing for inverse, equals 1 divided by what is in B2. Hit enter, and then autofill for the rest of them. So Excel did that for us quickly. Now I'm going to have Excel graph these three different sets of data. We'll see what those look like. Remember, when we're graphing Excel, we want to highlight the columns we want Excel to graph, making sure our X values are to the left of the Y values. So I've done that. Insert, scatter, and I want to have Excel draw a line for me. And there it is. Looking at it, we can see it's nonlinear. But to maybe prove it against the other data sets, I can use the R-squared value, which tells us how linear it is. Right-click on the points, add trend line, force a linear curve fit through it, display R-squared, and I've got an R-squared of 0.90, which is pretty low. Remember, 0.99 or greater is pretty linear. So this is further evidence that this is non-linear data. It's looking like it's not zero order because concentration versus time was non-linear. Let's see what natural log looks like. So now I've got to highlight time, and then to highlight a non-adjacent set of cells, I hold down Control. I can highlight natural log at the same time. Insert scatter. And not looking terribly linear. Let's see what the R-squared is. Add trend line. Display R-squared. 0.97. A little better, 0.97. Higher than 0.9. So it could be first order, but with that R-squared being less than 0.99, I'm not so convinced. Let's graph inverse and see if the R-squared is higher. And there it is. Of course, if this were a graph I was publishing, I would have units and values for the X and Y axis in a chart title. But the inverse against time is much more linear. The R-squared is 0.997. This is giving me confidence that it must be second order because the inverse of concentration against time is linear, or is the most linear. So it's second order. So now that we know it's second order, we can write the general version of the rate law. Rate will be equal to the rate law constant K, which we'll find in a moment, times the concentration of NO2 squared. There's our second order rate law. Final thing we need to do is to find the value and unit for K, substitute that in, republish the law, and then we're done. Remember, from a second order linear graph, or time versus inverse concentration, the slope is the rate law constant because that data set's already positively sloping. So the rate law constant is the slope. Meanwhile, slope is equal to change in y over change in x, rise over run. The y value is inverse concentration, so it's going to be the change in the inverse concentration over the change in time. So really, we could pick any two sets of data to find our slope. The further away, though, that data points are, the more valid the slope. And of course, if we used Excel, which I did, to graph the data and get the curve fit, I could get the slope from there, but that's not something you'd be able to do on the AP test. So I'm going to use the times of 0 and 400, the corresponding y values of 312, 0.5, and 100 to find my slope. So my y2 minus y1 is 312.5 minus 100, like I said a moment ago. x2 minus x1 is 400 minus 0. That's depicted here. And that comes out to 0.53. So that's the value for the rate law constant. Remember, this is second order. And we know that the unit for the rate law constant we'll have the exponent for molarity that is 1 less than second order. So there's going to be just 1 molarity in the denominator. It's going to be 1 over, because there's always seconds, times molarity. It could also have been published as seconds to the minus 1, molarity to the minus 1. Either is okay. So the final thing we need to do is to plug this value and its unit into the rate expression from above, and we're done with the problem. And there it is. The rate is equal to 0.53 seconds to the minus 1, molarity to the minus 1 times the concentration of nitrogen dioxide squared, or second order. And then just one more little thing about units, because you could see this. We know already that molarity is moles per liter. Inverse molarity, meanwhile, would be the inverse of that. It would be liters per mole. So molarity to the minus 1, or inverse molarity is liters per mole. That could be written, if we wanted to, as liters times moles to the minus 1. Bringing moles into the numerator means we've got to give it a negative exponent. So we could, if we wanted to, or maybe you'll just see this sometime, write the rate law constant for this in this format. And I'll show you what that looks like. So instead of 0.53 seconds to the minus 1, molarity to the minus 1, because we know molarity to the minus 1 is liters times moles to the minus 1, we can substitute in for that, and you end up with liters times moles to the minus 1 times seconds to the minus 1. So might see that, but it's okay if you publish it in one of these other ways above. So I've jumped ahead. I'm now on page 68 of the ebook, looking at the review questions, and we will do problems 2 and 3 together as our final 2 example problems for this lecture. So question 2 says the rate constant of a first order reaction is 4.03 times 10 to the minus 3 inverse seconds. What is the concentration, what concentration of reactant remains after 74.6 seconds, assuming an initial concentration of 0.3 moles per liter? This will be an integrated rate law problem. We will use the first order integrated rate equation, which has all these variables in it, including the one we want to find, to solve this problem. So we write out the integrated rate law for a first order reaction. That's going to be natural log. So natural log of, we'll say C, I'll put C in there instead of A in parentheses, equals, remember it's negative KT plus the ln of the initial concentration, C sub 0. Just taking a moment to identify the variables. That's the rate law constant, K, so we'll plug that in for K. The time is here in seconds. Remember, times need to be in seconds. If they aren't, convert them into seconds, unless the unit for time in the rate law constant is minutes, in which case the time could be in minutes. Just need to make sure those units agree. But the rate law constant unit for time will almost always be seconds. And then here's the initial concentration in molarity, like we'd expect. So it is the new concentration we're finding. It's the C in the LNC. Remember, that represents any concentration after the initial concentration, any concentration along that line. So I've got LNC is equal to negative 4.03 times 10 to the minus 3 seconds to the minus 1 times the time of 74.6 seconds plus the natural log of the initial concentration, which is 0.300 moles per liter, or molarity. The initial concentration also doesn't have to be the true initial concentration. It just has to be the earlier of the two. An earlier concentration can be thought of as the initial concentration. Everything on the right I got equal to negative 1.5046. I rounded it to negative 1.50. So to get the concentration, I've got to do inverse natural log, which is e to the. So I'm going to raise e to the negative 1.5. And when I do that on my calculator, I get 0.222, which makes sense. The concentration should be falling. So the concentration is 0.222 molarity, or moles per liter if we want. All right, we're back to those review questions. We're going to do 3 now, and that'll be the final problem we will solve in this lecture. So question 3 says the reaction between 2 B atoms or molecules yields a C and an A. It's second order. The rate constant is 0.15 liters per mole times minutes. Liters per mole is inverse molarity, by the way, because molarity is moles per liter. Liters per mole is inverse molarity. So this unit really is 1 over molarity times minutes. And minutes is in that rate law constant instead of seconds. So that means that the time that we'd need to plug in to the rate law equation would need to have minutes in it as well, which, as we read the problem further, it does. The initial concentration of B is 2 moles per liter, and what is the concentration of B after 45 minutes? So we're trying to find the final concentration here. We know the initial, we're trying to find the final. Let's do it. Since we're told this is a second order reaction, we will write the second order integrated rate law, or second order integrated rate equation. that has inverse concentrations in it. So I'm going to write 1 over C equals negative, this one has, remember, positive because the slope is already positive, for equals KT plus 1 over C sub 0. There's our second order integrated rate law. I've circled and identified the known variables. There's the rate law constant, of course, we talked about that. There's the time in minutes, and there's the initial concentration of 2 molar. So I'm going to plug those in, and then we'll solve for the final concentration, or C in this case. So there's everything plugged in. There's my rate law constant, the time, and 1 over the 2 molar initial concentration. From the right-hand side, I get 7.25. If the units for time cancel, then I'm adding inverse molarity to inverse molarity. So I get inverse molarity from, I take the inverse of both sides to get concentration. The unit will just be molarity. And that's what I've done. This -1 is saying I'm taking the inverse of both sides. And that gives me a final concentration of 0.14 molar. Just want to check to see if that seems to make sense. It started at 2. Quite a bit of time has elapsed. This is the decrease in the concentration over time. Makes sense to me that it might be that low after 45 minutes. So there's our final answer. Job well done, folks. That is a wrap. I hope you're having a nice day, whatever it is you're doing. And as always, work hard, be kind, be humble, and make the world a better place. See you soon, folks.